A very good evening to every one of you. Okay, now we are back with the second lecture on coordination compounds. Okay, so we have stopped where we have stopped. We are going to continue from there. Okay, some of the important terms related to coordination compounds. Last class we have studied like what is mean by ligands, what is coordination, what is the difference between coordination compounds and the double salts. All those things we have studied in the last lecture. Those who have not watched the last lecture, you can go to my channel Kumar Sir and watch the first lecture on this chapter. Then you can come down to this. Okay, well, to start with, let us start. Today in today's lecture we are going to study first types of ligands. So how many types of ligands are there, we are going to study today. Okay, so types of ligand, the first ligands we are going to discuss is unidentate ligands. By the name itself it is clear that uni means what? Single, one. Okay, it is also called as monodentate ligands or unidentate ligands. Okay or not? So what is the definitions for it? Let us first go through, then I will come to the explanations. Sorry. So ligands which can coordinate to the ions, the ligands which can coordinate to the central ion, central metal atom, that is what we are talking about. The ligands which can coordinate to the central ion through only one donor atoms, means those ligands which can coordinate, which can make a bond with the central atom only through one atom, donor atoms, that is only through one donor atoms, are known as unidentate ligands. Some common examples are NH3. For example, I will let you understand in an easy way. For example, CONH3 6 times. Okay, CONH3 6 times. So you can see here clearly hydrogen does not have the capability to form two double bonds. So here whatever bonding will be done, it will be done between cobalt and nitrogens only. Okay, so here in this you can see clearly ammonia, N is the donor atom. N is only going to make a bond with the cobalt. That this is central metal atom. That is what we have written, central ions. So with the central ions, only nitrogen is going to make a bond. Okay or not? So this NH3 is a what? Ligands. It's a ligands. And in this ligand, which one is the donor atom? Nitrogen is the donor atoms. So this kind of ligands we call it as what? Unidentate ligands or monodentate ligands. Okay, why? Because in this ligands only nitrogen act as a donor atoms. Other one it is not capable of acting as a donor atoms. Okay or not? Other example here is H2O. In H2O you will see that oxygen will act as a donor atom. Oxygen alone is capable of forming a coordinate bond with the central atom. Okay, another one, Cl, that means all the halogen groups, they are capable of forming unidentate. They are also an example of unidentate ligands. NO, in NO you will find that the bonding will be done through N, not through oxygens. So here this is also an example of unidentate, because here all bonding will be done only through nitrogen, not through oxygens. Another example is NO2 negative. Here also bonding will be done through N. So you have understood, I suppose, what is unidentate ligand. Unidentate ligand are those ligands in which only one atoms will act as a donor one, others it will not be acting as a donors. Like example here NH3, you can see that nitrogens only will be forming a coordinate bond with cobalt, not the hydrogens. Okay or not? So this kind of ligands we call it as what? Unidentate ligands. Hope you have understood. Next type of ligands is what? Didentate ligands. So this is also known as didentate ligands or bidentate ligands. Okay or not? Both the way same. Bidentate ligands or didentate ligands. So bidentate ligand, by the way, by the name itself it is clear. Here the donor atoms will be two. Means the coordinate bond will be formed through two through two atoms. Okay, one common example is oxalate ions. It is represented as OX. So in oxalate ions, this is oxalate ions, COO negative single bond C, double O, negative. Here they can form a coordinate bond through this oxygen and through this oxygen. So there are two positions through which the coordinate bond can be formed. So this one, oxalate ions, is an example of what? It's an example of didentate ligand because it is capable of forming a coordinate bond with the central metal atom through two positions. So it is called as didentate ligands. Okay. Another example of didentate ligands is ethane 1,2 diamines. It is represented as En. Okay, this one you remember it, very common examples. Okay, it is represented as En or it is also called as ethylene diamines. Okay or not? So here you can see CH2NH2, CH2NH2. So when it will form a coordinate bond with the central metal atom, remember the bond will be formed through this N and through this N. Okay, the coordination bond will be through the central metal atom. They will form only through this and this. So there are two positions or not? So here also you can see that there are two positions through which coordinate bond can be formed. So this kind of ligands we call it as what? Didentate ligand. Similarly, there are tridentate, tetradentate, pentadentate ligands are also there. The tridentate will be what? Through three sides they can form a coordinate bond. So those will be called as what? Tridentate. Tetra means through four sides there will be four donor atoms through which they can form a coordinate bonds. Okay, and so on. So I hope you understood the concepts of types of ligands. Okay. If you have any doubt, please feel free to comments in the comments box your doubts. Okay. Now moving on. Next topics which we are going to discuss today is chelations. Okay. So what is chelations? First, let us try to understand. Then we will go in the detail. Okay. So chelations. When a di or polydentate, di or poly means those ligands which are capable of which are having two donor sides, or poly means more than two donor sides. Okay, ions. Ligands uses its two or more. So when a di or polydentate ligand uses its two or more donor atom to bind to the same central metal atom, it is called as chelations. Okay. For example, we will take the same example of ethylene 1,2 diamines. So this is ethylene 1,2 diamines. Here you can see, suppose any metal atom is here. Let's take an example of Cu, for example. Okay, so you can see that there is two donor atom. One here is N and here also is N. So this is two donor atoms are there. These two donor atom also, they are forming a coordinate bond with what? Forming a coordinate bond with the same central metal atoms. So as a result, they are forming a closed structure. Okay, they are forming a closed structure. So they are called as what? This is called as what? Chelating ligands, and the phenomena is known as chelations. I hope it is clear. Once again, those ligands which are capable of forming a which are having two donor atoms or more, when they form a coordinate bond with the same central metal atoms. This N also is forming a coordinate bond with Cu. This N also is forming a coordinate bond with Cu. They are forming a coordinate bond. Two coordinate bond they are forming with the same central atom, leading to the closed structure. So these kinds of ligands, we call these kind of ligands we call it as what? Chelating ligands. Those ligands, when they form a coordinate bond and leading to the closed step structure, they are called as what? Chelating ligands. And the process and the phenomena we call it as what? Chelations. Hope it is clear to you. If you have any doubt, feel free to ask your doubt in the comment box. Okay. Now let us move to further in the chapters with the next topic. We are going to do is denticity, ambidentate ligands, and coordination number. See, these are the easy things, but the dear students, some of you might be knowing, but what to do? Easy things only we used to forget more, right or not? So that's why I want to go step by step. Okay, it may be a little long, lengthy video, don't mind for it, but let us go step by step. Even if you know also, those who know, you can move the video forward and go ahead. Okay, or else you can watch it properly so that your revision also will be done, because ambident you have studied in class 11, coordination number also you have studied, but still as the revisions, let us do it properly. Okay, step by step let us go. Then this chapter is very interesting. Okay, let's come to denticity. What is denticity? In a simple language, let us try to understand. It is the number of donor sites. Listen properly. It is the number of donor sites present in any ligands. Okay, so what is denticity? Denticity is nothing but number of donor sites present in any ligands. So in unidentate ligand, what will be the denticity? 1. Denticity will be 1 because the number of donor sites is only 1. So denticity is 1. In bidentate ligands, what will be the number of donor? What will be the denticity? 2. Example, you can see here unidentate H2O. So it can only donate through O, oxygen. So denticity is 1. NH3 ammonia, it can only donate through N. So here denticity is what? 1. So bidentate ligands example CH2 NH2 CH2 NH2, that is, this is nothing but it is EN, ethylene ethane 1,2 diamines, right or not? We have already discussed earlier. So in this you can find that you will see that the donor sites are 1, 2. So denticity here is how much? 2. Okay, I hope you got it. It's very easy. Okay, now coming to ambident ligands. Ambident ligands, as I have written here, marked here important. It is very important for your board examination. It comes for 1 mark definitions. Okay, so ambidentate ligands. What is ambidentate ligands? The monodentate ligands. Okay, that means unidentate ligands. So the monodentate ligands which can coordinate with the central atom through more than one site are called ambident ligands. Means what? Let us try to understand. See here CN, cyanide, right or not? Why? Because the coordination is done through C, so it will be called as cyanide. So it is unidentate because it is doing the coordinations only through C. So it is unidentate ligand. So in these ligands, you see here coordination is done through C. M here represents metal. It can be anything. Here M represents metal. Don't get confused. It can be Cu, Co, anything. Okay, Ag. So that's why as a common I have written M. M represents metal. So here this Cn cyanide, it is coordinating, means it is forming a coordinate bond through whom? Through C. Again same cyanide, it can form a coordinate bond through whom? Through N, right? So same cyanide Cn, it is capable of forming coordinate bond through C as well as through N, but both will not happen at the same time. It will be different. Okay, it will not here also it is forming bond through C and here also forming bond through N. That is not possible. Separately it will be. Okay, so here as you can see, the cyanide is forming coordinate bond through C, okay, with the central metal atom. This is central metal atom, and here you can see the cyanide is for isocyanide. It is forming a bond through N. So both are same compound, but they are capable of forming the coordinate bond through both the sides, through C also, through N also. So this is an example of what? This kind of ligands we call it as what? Ambident ligands. Okay, another example, let us see. NO2, nitrite. Okay, so here you can see nitrito group. Okay, so in this you can see here, first case it is forming a coordinate bond with the central metal atom. This is nothing but central metal atom. It can be Cu, Ag, Co, anything, any metal it can be. Okay, so it is forming a coordinate bond through whom? Through N in the first case. So the name is nitrito dash N. Dash N represent means coordination is done through N. That is the meaning of this dash N. Okay or no? In the second case you see coordination is done through whom? through oxygen. So the name is nitrito O, means O represents here, O represents what? The bonding coordinate bond is formed through oxygen, and here N represent coordinate bond is formed through N. So you can say in general NO2 is capable of forming coordinate bond through N as well as through O, but not at the same time. So this NO2 is what? It's an example of ambident ligand. So it will be called as what? Ambident ligands. So is the case in CN. CN is also an example of ambident ligands. So once again I will tell you what is ambident ligands. Ambident ligands are those ligands which are capable of forming coordinate bond through both sides. Okay or not? But not at the same time. Okay, such ligands we call it as what? Ambident ligands. Okay or not? It is capable of forming bond through C also. It is capable of forming coordinate bond through N also. So it is called as what? These ligands will be called as ambident ligands. I hope you have understood. Now let us move to the next one, coordination number. The next topic is coordination number. This all of you might be knowing, but let's do it again. Coordination number. So what is coordination number? The total number of ligands attached to the central metal atom. Which one is the central metal atom? These are called as central metal atom. Okay or not? So total number of ligands. So ligands are this or not? This is CN is a ligands. This one is ligands. This one is ligands. Already I have explained you in the first lecture what is ligands. Okay, those who have not watched it, you can go to my channel Kumar Sir and watch it. Okay, so total number of ligands attached to the central metal atom. So this is central metal atom. Total number of ligands attached is how much? 2. So this 2 is called as what? Coordination number. Got it or not? So total number of ligands attached to a central metal atom or ions is called as coordination number. So here you can see this is a complex compound or coordination compound, AgCN 2 times negative. Okay, so Ag ka coordination number here will be what? 2. How many Cn are there? 2. So coordination number is 2. Here PtCl6. So what is the number of Cl here? 6. Means 6 Cl will be forming a coordinate bond with the central metal atom. So coordination number of Pt will be what? 6. I hope you have understood it. Okay, so let us now again all of you can take it down, and then we will move on to the next topic. Okay, so now moving on to the next topic, we are going to discuss now oxidation number. So this topic is also not that new. We have already came across in class 11, but here the things are a little different, so that's why I thought of teaching you. Okay, what's the oxidation number? Let us first know. So oxidation number is the charge carried by the central atom when all the ligands are removed along with the electron pair that is shared with the central atom. For example, here CO is there, cobalt. The ligands is what? This is central atoms. So the ligands here is NH3, and how many NH3 is there? 6. So when this NH3, 6 NH3, it will be removed from here. If it is removed from here, along with the electrons, what NH3 is carrying electrons, so that electrons along with that ligands, if we are removing, then what charge will come on this? What charge will be left on this CO? That is called as what? Oxidation number. So what is oxidation number? That means what will be the charge left here? It will be +3. Once again, students, I want to tell you what is oxidation number. So oxidation number in coordination compound is the charge which will be left on the central atom when all the ligands along with their sharing electrons will be removed. When all the ligands are removed, suppose here ligands was what? NH3 6 times. It was there or not? So when I will remove this NH3 6 times, these ligands, when I will be removing it totally along with their electrons, so after removing that, whatever charge will be left for CO, that is called as coordination, that is called as oxidation number. I hope it is very much clear to you. Okay, so here you can see CONH3 6 times 3 positives. So what will be the oxidation number of cobalt? Oxidation number of cobalt will be 3. Now 3 positive. How it is 3 positive? I will be telling to you. Okay, how to calculate we are going to discuss next. I hope you have understood what is oxidation number means. Okay, now coming to calculations of oxidation number. In class 11 also you have learned this oxidation number, how to calculate, but that was for simple compounds you have learned. Here we are going to learn for a complex compounds. Okay or not? So let us take one example, NiNH3 6 times 2 positive. So this is the compounds. So what we will do, first of all we will assume we don't know what is the coordination number of the metal, okay, the central atoms. So what we will do, let the oxidation number of central metal, that is Ni, be x. We will assume it like this as we have done in the class 11. Okay, after that what we are going to do, x, that is central atom ka oxidation number x, plus ligands. This is ligands, right? So how many ligands are there? What is the coordination number here? Here coordination number is 6. So 6 into what is the oxidation number of NH3? Dear students, these points you should remember it, because if you don't know this, it will be very difficult for you in this chapter. I will give you the list also. Maybe after 1-2 days I will give you the list. NH3 oxidation number, since NH3 is what? Neutral. So oxidation, since NH3 is neutral, therefore oxidation number is 0. NH3 is neutral, so oxidation number is 0. So X is the oxidation number of Ni, plus 6. What is the coordination number? 6. So 6 into what is the oxidation number of NH3? 0. So into 0. And what is the charge here? Plus 2. So that one will write equal to plus 2. If it is minus, we will write minus 2. Okay. Then next, 6 into 0 is what? 0 only. So X equal to how much we are getting? Plus 2. So Ni, that is central atoms oxidation number of Ni is what? Plus 2. I hope you have understood it. Now let us go to the little bit. This was pretty easy. So now let us go to the next one. Okay. So COClNH3 5 times 2 positive. So now we are going to calculate the oxidation number of which one? What is the central metal here? Cobalt. So cobalt oxidation number we are going to calculate here. So what we will assume? Let oxidation number of cobalt be X. So X plus Cl is how much here? Cl is only 1. So minus 1 we have written. Cl oxidation number is minus 1. So minus 1. And NH3, as I told you, it is a neutral. So oxidation number is what? 0. So 0, and how many NH3 is there? 5. So into 5. Points are clear. I think I am not too fast. Is equal to what is the top? What is the charge here? Plus 2. So we'll write here plus 2. So this minus 1 plus minus minus. So this minus 1, if you shift it this side, then it will become what? Plus. So plus 2, and this minus 1 comes this side, then plus 1. So it becomes 2 plus 1 equal to 3. So the oxidation number of cobalt here is what? 3 plus 3. I hope you are getting it. Okay. Next, third example, FeC2O4. This C2O4 is nothing but oxalate ions. It is like this: COO negative, COO negative. Okay or not? 1, 2, C2 carbon, 4 oxygen. So we are writing in short C2O4. Okay. So this is nothing but oxalate ions. Okay. So FeC2O4, 3 negatives. Okay or not? So first of all, you should know what is the oxidation number of C2O4. So I have given here oxidation number of C2O4, that is oxalate ion, is minus 2. These points you should remember it. Okay. So let the oxidation number of Fe be X. So we are considering that the oxidation number of Fe is how much? X. So we have written X plus how many oxalate ions are there? 3. So 3. And what is the oxidation number of oxalate ions? It is minus 2. So 3 into minus 2 equal to, what is the charge here? Power given here minus 3, so it will be minus 3. So 3 into minus 2, it will become how much? Minus 6, which will be equal to minus 3. So this 6, if you shift it this side, then it will become what? Plus. So minus 3 plus 6, it will give you how much? It will give you plus 3. So x is equal to plus 3, and x is the oxidation number of Fe. So oxidation number of Fe is equal to plus 3. I hope all of you have understood it and you are enjoying the lecture. Okay, next, at the end of the video, I will be giving you some works to be done. Okay, so if you have understood, definitely you will be able to do those works. Okay, so now let us move to the next topic. So the next topic we are going to discuss now is homoleptic complexes. So what is homoleptic complexes? Let us try to understand. Complex in which the metal is bonded to only one kind of donor group. Those complexes in which the central metal or the central atom is bonded to only one kind of donor is called as what? Homoleptic. Homo means same, okay, or not? Same kind of donor. If it is attached to the central metal atom, then we will call it as what? Homoleptic complex. Example, NiNH362 positive, right or not? So here I have shown the coordinate bond formations here. Let us see. So Ni, this is the central metal atom, here central metal Ni, okay. So you can see that this Ni is only bonded through whom? N, and N, right or not? So throughout the structure you can see that the central atom is only bonded to one kind of donor, that is N, nitrogens, right or not? So this kind of complexes we call it as what? Homoleptic complexes. Okay, so I hope you have understood this very basic thing. If you are taking down the notes, definitely you should take it down. So you take it down this one also, so that it will be very clear for you. Okay, now heteroleptic. Hetero means different types. Okay, maybe not one types, it may be different. It is not same, it is different. Okay, not hetero means different. So heteroleptic complexes. So you can see here complexes in which the metal means central metal, okay, the metal is bonded to more than one kind of donor group. The central metal is bonded to more than one kind of donor group. Example, COCl2NH3 4. So here it is very clear that this is central metal, that is CO. It is bonded to chlorine, and it is going to bond through chlorine, as well as it is going to bond through N. So here the donor atoms are 2, chlorine and N. So that's why this is an example of what? Heteroleptic. If you are not getting it, you can see the structure downside. See, cobalt is the central metal, so it is attached through N, right? 4N, and it is also attached with what? Cl. So this kind of complexes we call it as what? Heteroleptic complexes, in which the donor atoms are not only one kind, but it is different types of donors are there. So we call it as heteroleptic. Here only same kind of donor atom is there, so it will call as homoleptic. Okay. Now before starting the IUPAC naming in this IUPAC name or IUPAC name in this coordination compound, which is a very important part of for your exams IUPAC. So we should learn some basic things, okay, regarding IUPAC. In that, one basic thing comes is types of ligands on the basis of charge. We have seen ligands are unidentate, bidentate, and all those things. That is on the basis of number of donors. Okay, but here we are going to classify ligands on the basis of charge. Okay, means if they are on the basis of charge, we are going to what we are going to do, we are going to classify the ligands. So the first type of ligands here we are going to discuss is negative ligands. Okay, so negative ligands, what will be there? The IUPAC name of the negative ligands ends with letter O, means when there is a negative ligands. For example, I'll give you NiCl6. okay, NiCl6. So this NiCl6, this Cl is what? It's a negative ligand. So when you are writing the IUPAC name of this, so what will be the name of this? The name of this is what? Chloride. We write it like this or not? Chloride. But when you write the IUPAC name in coordination compound, then what will happen? This E will be replaced by O. That is the meaning of it. The IUPAC name of negative ligands ends with the letter O. So it will be chlorido. We will be writing it as chlorido. I hope you are understanding it. Similarly, you see here I have given fluorine negative. So when fluorine will be there in the ligands positions, then its name will be written as what? Fluorido. If Cl is there, then right now I have shown you, it will be written as what? Chlorido. If NO2 negative is there, then it will be written as what? Nitrito N. As I have already discussed with you earlier, that N represents that the bonding is done through N. Okay, nitrogen. ONO. So it is written as nitrito, but here bonding is done through O. So O. Okay. This is what? Sulfate. SO4 2 negative, so it is sulfate, but it is what? It is a negative ligand, so the name will be written like this: sulfato. E will be sulfate. E is there or not at the last? It will be replaced by O. This is what? Cyanide. This is a negative ligands. Okay or not? So cyanide, CYANIDE, cyanide. So that E is replaced by O. This is what? Carbonate. This is also negative ligands. So CO2 negative is there. So it is carbonate. Carbonate. CARBONATE is there. So that E will be replaced by O. Carbonato. Okay. So O2 negative is there. It is oxide. It is read as oxide, but it will be written as oxo. Okay. Got it or not? So this is how we will be naming the negative ligands, my dear students. In your textbook, there is a list of negative ligands. You can go through it. What is the name of each negative ligands? Okay, it is not possible for me to discuss everything here. I have given you the sample of negative ligands, how it is named. Okay, at the last, E will be replaced by O when you are writing the IUPAC name. Okay, I hope this is clear. Now there are two more types of ligands, that is positive and neutral ligands. So let us discuss it and then we shall switch to the next topic. Okay. Remaining types of ligands that is on the basis of charge are: one is positive, second one is positive, and third one is neutral. Let us discuss today properly. So positive ligands. So whatever positive ligands will be there, like when you are writing the IUPAC name, suppose you, and here you have got NO positive, okay, 3 times. So if you got like this, so when you will write the name of this NO3 positive, how you will write that one we are going to discuss. The IUPAC name of the positive ligands ends with yum. So when you are writing the IUPAC, this is nitronium, okay or not? So so when you are writing the name of IUPAC name of this, so how you write NO positive? The name should end with what? Yum. IUM. So nitrozonium. Okay, not you will write the name this way. This is the positive ligands rules. Okay, so NO2. So nitro. So this is what? NO2 positive. Okay or not? So here you will be writing here nitronium. Okay or not? Since it is positive, it will be written as nitronium. If it happens to be negative, then it will be written as what? Nitrito. Okay. So if positive, then nitronium. NH2, NH3 positive. Actually, it is hydrazine. Okay, hydrazine. You might have come across, or if not, then you will be doing it in the organic part. Okay, NH2, NH3 positive. It is hydrazine, but since it is a positive ligand, so it will be named as, when you are writing the IUPAC name, you will write as hydrazinium. Okay, hydrazinium. You will be writing like this. Okay, so I hope you understood how the positive ligands has to be given their IUPAC name. Now coming to the neutral ligands. So neutral ligands, when we are writing the IUPAC name of the complexes, and if neutral ligands comes there, then how to write? What is the rule for it? The IUPAC name of the neutral ligands remains unchanged. Means neutral ligands, whatever name is there, that name only you will be writing in IUPAC only. IUPAC, okay or not? So whatever their common name is there, that whatever name they have, that name only you will be writing in IUPAC as well. So CH3NH2. So this common name, if you can see, then methylene amine. So we'll write as methyl amines only, okay or not? Next, CH2NH2, CH2NH2, that is nothing but ethane. 2 carbon is there, so ethane, and 1 positions amines and second position also amines. So ethane 1,2 diamines. Its short form is what? En. So whatever name it has, same name will be writing. Why? Because it is a neutral compound or neutral ligands. Okay or not? Similarly, C6H5N. So this one name is what? Pyridine, and its short form is PY. In the book, when we are going to do IUPAC, that time you will find many symbols like this, PY, EN. So you should know the name. It is called as pyridine. So for the neutral compounds, for the neutral ligands, the IUPAC names remain unchanged. Positive ligands, the name ends with yum. For negative ligands, the name ends with O. Now coming to the some exceptional cases of neutral ligands. Okay, in some exceptional cases, the name will change. What are those 5 exceptional cases? Let us see it. Okay, if H2O is there, H2O is what? Water. It is neutral, so it will be written as what? Aqua. Instead of writing water, we will be writing as what? Aqua when we write the IUPAC name. NH3, it is will be ammonia, but when we are writing the IUPAC name of it, we will be writing it as what? Amines. These things, these 5, you have to remember it. It will be required very much in the IUPAC naming. NO, so it is what? Its name will be what? Nitroxide. Okay, my R and S is little same, so don't get confused. So it will be nitroxide. And CO, it will be what? Carbonyl. The name of CO will be carbonyl. And then CS. So this name will be what? S represents thio. So thiocarbonyl. Okay, no? So these are the some exceptional cases in neutral ligands. Okay, so I hope today's lectures you have understood. And my dear students, if my video lectures are benefiting you, and if there is some friends of yours who are studying in maybe other schools, other institutions, or other state, but they are in need of help, they need some sources to learn, feel free to share your chemistry channel Kumar sir with them. Okay, and let them also subscribe my channel and enjoy the free lectures. Okay, so dear students, come onto the channel, watch the full video once, twice, thrice, so that you can understand properly. Don't simply come, take it down the notes and go away. You have to understand also. If you have any doubt, feel free to comment in the comment box. Okay, I hope you have all enjoyed it. Okay, now we will see you in the next class, with the remaining lecture of these chapters. Thank you so much. God bless.